Okay, so it's my great pleasure to present our next speaker, Professor Kuchment. So you see the title of his talk, and please go ahead. Thank you very much.
Thank you very much for the nice invitation. It's an honor. Rostov has always been a major center of mathematics. I have known personally and through their works many mathematicians from Rostov, and actually my wife defended her PhD in mathematics in Rostov in 1976. So it's an honor. So what I will do, first of all, I want to say that I decided to give a colloquium style talk rather than a technical seminar talk. Since the seminar talk would assume that you are all experts, at least to some degree in this area, and I would give you technical details. Since I don't want to assume this, I will give a survey type talk just to entice you to dive into this beautiful area. There is some echo somewhere. Probably someone's microphone is not muted, right? So I will be talking about some novel developments in mostly medical imaging, although it has, as you will see, industrial and homeland security and many other applications. And this is fantastic areas that I have accidentally started working 30 plus years ago in Voronezh, and then I and my co-authors and students and many others discovered that it's such a fantastically interesting and challenging area of mathematics that I have never left it. And it keeps developing. Every new development brings new mathematical problems, usually difficult, beautiful, and it's fun to deal with them. So the main idea of medical imaging, and this is the cartoon of my head cut off that I drew when many years ago they were taking scan of my head, expecting, just checking whether I didn't have brain tumor. Also, all my friends claimed that brain is the organ on which I cannot possibly physically have a tumor, but that's the idea, to cut off my head and to look inside, which is certainly not very, very useful. So instead, they did scan, and that's what they saw. That's the brain scan. Certainly, it's not mine. Mine probably is even smaller, but this is a brain scan of Homer Simpson. And what does it have to do with mathematics? The thing is that probably you all realize, and I will mention it also, that the machine doesn't produce any picture. It cannot actually get inside of your head and see what's going on inside. So let me first of all. So this is, as I said, this is a fantastically beautiful and interesting area of mathematics involving all mathematics I have ever seen in my life and more. I will make a disclosure that I will not show you the references, since there are dozens or maybe hundreds of leading mathematicians and physicists who have worked on this and still work on this. So I just flash a list of at least some names. Again, there is someone's microphone is working, interfering. Sorry. So I will not refer to the results, to the authors of the results, and there are too many of them. And I will just refer to a few survey articles. So looking at the authors, don't think that it's all my work. As I said, many people all around the world created this. These are just surveys where you can find the references, if anyone is interested. Actually, I will submit the PDF files, so if anyone would be interested, I submit the PDF file of this presentation to the organizers. So here is my overly optimistic, probably impossible to complete plan. I will try to describe what do medical, industrial, homeland security imagings have to do with mathematics, in particular with PDEs. What were some difficult mathematical and physics issues that triggered some new questions, and I will address only those. And hopefully I will at least briefly address 3 of them. One about hybrid imaging, and I like calling it, and you will see why. You probably all know the famous Marcus question, can one hear the shape of the drum? And I call it, can one hear the heat of a body? And you will see why it is. Then some problems with internal information and some novel mathematical and engineering issues coming from trying to work with data which are very noisy. Okay, so what is the idea of tomography? It's called tomographic image. Tomos means slice in Greek. So originally, all those types of imaging were done slice by slice, although now there are many fully 3D images. So the idea is that we have this non-transparent body, which we want to pick inside. Where is my pen? You have somebody, and there is something, let's say, hard inside that we want to see. But we cannot get inside. We don't want to cut open our patient. So what we do, we need to send something from exterior, something that penetrates. It can penetrate, sorry, this body. It penetrates, but then there is something that comes out. And we are sitting outside, looking at this, and we know what we sent in, and we observe what comes out. And from this exterior observation, we want to figure out what is inside. So it's not anything like usual X-ray picture, which is just actual picture. We don't get a picture, we get bunch of data, and you will see some kind, what kinds of data in particular. This is stock effect. I never had any cough lately, but don't worry, it's just a virus. Okay, so what can we send? We can send zillions of things, and people use all of them in different circumstances. We can send X-rays, ultrasound, we can use gamma photons, neutrons, light, electrical currents, magnetic fields, etc. The question is, why do we need so many? And all of them are used, and many others that I haven't mentioned. Why do we need that many? Since they see different things. For instance, X-rays essentially tell you what are the densities inside, the densities of tissues inside of this body. That's roughly what X-rays tell you. Ultrasound sends the sound speed inside of the body. Laser light, if you shine it, senses optical properties of the body. Electrical currents would sense electrical conductivity inside of the body. These are all different physical parameters, and they might not be related to each other at all, or if related very vaguely, and in different circumstances you want to know different ones. That's why people keep inventing new ones. Another difference is that some of them are very costly and some are cheap. X-ray machines are very costly. Ultrasound machines and laser light machines are cheap. Safety. X-ray machines, no matter what radiologists told us, are not completely safe. One X-ray scan is like about 80 usual X-ray pictures. Ultrasound is safe. Laser is safe. Certainly, if you pick appropriate frequency and intensity so you don't burn the patient. The same about electric currents. Since electric currents used in imaging are so tiny that you don't feel. But these are not the issues I will be discussing. I will try to concentrate on the following three issues that I have in red. Contrast. What does it mean, contrast? I mentioned that X-rays feel the density of the tissues. So, for instance, imagine that these tissues that I showed as a heart and the one outside they are different, but they have almost the same density. Then X-ray picture will not see any difference between this heart and surrounding tissues, since they look the same to X-ray. This means that there is no contrast. Contrast is how different parts of the object react to your radiation, to your waves. And so X-rays, they have to fight with very low contrast, sometimes a couple of percentage points. But I will show you pictures, you will see that they do this extremely well. So this is contrast. On the other hand, so if we want to have your imaging technique to have good contrast, preferably not 1-2 percentage points or less, but maybe 50%, 100%, maybe even more. So you see clearly the difference. However, since you are not inside and you don't detect locally those parameters, you only see what comes back. The question is how well you can see, how sharp you can see the interior features outside. So can you recover the sharp boundary of objects like heart, lungs, especially small blood vessels? Can you see them sharply? In other words, what small details can you see? How small details? We want to see at least in sub-millimeter resolution. And it's not only about seeing sharp details. Somehow, this is mathematically, intrinsically related, actually equivalent to stability of your technique. What does it mean, stability? You do experiment. So your data is experimental, and therefore it is plagued by errors. So stability means that small errors in what you get, what you measure, produce only small errors in your picture. That's stability. Somehow one can show that seeing sharp details, which means resolution is the same as stability. And another thing is that in some, you always have noise. For instance, you send some gamma, observe some gamma photons. Many gamma photons are flying around just by themselves. And so you have exterior noise. In medical imaging, usually it is not very big noise, although sometimes it gets annoyingly large. In other areas, as I will tell you, it could be huge. The signal could be 1,000 times smaller than the noise. What can you do? So these are the issues I try to deal with. Okay. Now, what I just described, I drew a cartoon. So this is your object in pink, and you can, for instance, if you use ultrasound, what you do, you listen from outside. You're listening to sound coming out of this. If you use light, you look, you observe the light coming out. In X-ray CT, you have the source of X-ray here. By the way, do you see my cursor moving, my mouse point?
Yeah.
Yes, we can see it.
Okay. So this is the source of X-ray, and it sends a very thin beam. I will not describe how they got thin beam. It goes through the body, and there is detector on the other side, which detects what is the intensity of the beam coming in this direction. There is another medical imaging and industrial imaging problem where your source is not controlled by you. For instance, you're a patient, you are given some medication which is labeled by a very tiny portion of radionuclide, and it starts emitting from inside of your body. So we don't know where the source is. Actually, we want to know where did it go and how intensive it is. So you don't know the source of this noise or of this signal, and it emits a ray and gets to the detector. So these are cartoons, and here are some actual machines. For instance, this is one of the types of tomographic scanners, probably X-ray or so-called SPECT. This is a detector gate on border crossing where they try to detect whether they try to detect whether this truck has hidden any weapons-grade uranium, for instance. And this is so-called Compton camera. I will be talking about it if I reach it later. Okay, before going to mathematics and everything, I want to persuade you that it can work. Since it's not, when I started working on this, I was not sure. But look, this is my favorite picture. This is a tomographic picture on the left of a slice of human knee. No one cut this knee open. The patient is still alive and his knee is intact. But this is tomographic reconstruction. Now, if you see this, I don't know whether you see this well, on my screen it shows how tiny details we can see. It is amazing, all tiniest details. It is better than if you indeed cut the knee open, since you would have a lot of blood and everything around, and you wouldn't have such nice picture as this. So it's amazing resolution. Now, the contrast was not very high here, but still you see the machine and mathematicians who worked on the collected data did great job. This is example of industrial applications. This is a chunk of composite material, and it has not been cut open like you see here. There is no cut. It is mathematical reconstruction of the interior imaging, and you see some defect here and here. And this is interesting. Unfortunately, I didn't have space for a bigger picture. What is this? And the bigger picture, you would have seen that the top plane is the Earth unfolded into the plane. That's a planar map of the Earth. And what those red blobs show, they show magma coming from deep from the core up to the surface, the volcanoes. And this picture shows colder magma going down. Certainly here we didn't use X-rays or neutrons or sounds or anything, but what people used here was acoustic waves created by earthquakes. Since we don't want to create such severe acoustic waves that they penetrate that deep, you would have to explode many nukes. You don't want to do this, but earthquakes are more powerful than nukes, and there are plenty of them, so we could use this. And this is pretty bad picture. Bad in the sense that it's also a picture of interior of human chest, and it is very fuzzy. You compare with a picture of the knee, and you don't see any details. It's all fuzzy. It's all details are blurred. So this is, as I said, but you see the colors are very contrasting. Unlike in the knee, these are little bit different shades of gray. Here, the huge contrast, red to blue. So the contrast was perfect, but resolution, the sharpness is awful. This is what you see when you send electrical currents. And similar thing, if not worse, is when you send the light. Blurry picture, but the contrast actually is wonderful. And here with the knee, the contrast was pretty bad, but resolution is fantastic. Okay, now what does it have to do with mathematics? The thing is that all those procedures boil down mathematically to the following. There is some differential equations, partial differential equation inside of the body, and you know how it looks like. For instance, it could be this transport equation of heat equation, or this elliptic equation. Oh, I don't need this parenthesis. But what you don't know the coefficients. For instance, this in transport equation, this absorption coefficient mu, or source coefficient f. In wave equation, we don't know this coefficient c that correspond to the speed. In here, the coefficient d could be, if you use light, it's diffusion coefficient, and mu will be absorption. If you use electrical current, this d will be conductivity. So in all those cases, you have differential equation inside of the Earth domain. You know how it should look like, but you don't know the coefficients. What you can do, you can trigger some solutions, imposing some boundary conditions, and see the outcome. What does it mean, the outcome? For instance, for elliptic equation, you can prescribe Dirichlet condition on the boundary and measure the Neumann data resulting, or the other way around. In electrical tomography, this means that you create currents on the boundary and then measure what are the resulting voltages, or vice versa. Now, I told you that there are methods that have very good resolution. They see sharp details, and there are that don't. And mathematically, there is very, very clear distinction. If your equation is of kind of hyperbolic type, transport equation, hyperbolic equation, and this is a case of X-rays, gamma rays, and ultrasound, then resolution is great. And as I remind you, it means not only seeing sharp details, sharp boundaries, small scale resolution, it also means that small errors in the data don't do much damage. And what is the reason? The reason is that all those equations, they propagate their solutions. The most important is that they propagate singularities of solutions. So if you have any singularity inside of the domain, and singularity clearly would correspond, for instance, to the shape of the heart, or a bone, or something. All sharpness means singularities. These equations propagate them to the boundary. And so you feel somehow those singularities on the boundary. Remember, you are sitting outside. And if you deal with hyperelliptic equations, like, for instance, this elliptic equation, which is the case when you use light, other frequencies like microwaves, or electric currents, the situation is bad, since we know that smoothness for elliptic equations is a local property. So if you have a singularity hidden inside, it will never propagate to the boundary. So what it means that what you are looking for is a function which is singular, but what you measure is very smooth. In the worst cases, it's analytic. In a little bit better cases, it's infinitely differentiable. But even any smoothness is bad. Since I will not return to this, I need to explain why it is true mathematically. Since if what you measure the operator that takes some unknown interior function, mu, f, c, d, and maps it to what you measure on the boundary. And if there is no propagation of singularities, it means that your operator is very smoothing. It maps non-smooth functions to very smooth one. The smoother, the worse. Why the worse? Since the standard Sobolev embedding theorems tell you that in this case, I remind you what you want to do with this operator. You want to invert it. And embedding theorems tell you that if your operator is smoothing, if it increases the smoothness of functions, then its singular values decay. And the smoother the output, the faster decay. Finite differentiability of your data that you collect means decay, polynomial decay. Infinite differentiability of what you collect means decay faster than any power. And if your data, heavens forbid, is analytic, it means that the singular values decay exponentially. Now, if you have dealt with numerical analysis, you are very well familiar with singular values, but somehow in old days, at least in my linear algebra, they have never been mentioned. So I learned about them only when I started doing some numerics. But if you have done operator theory, you also know them. These are the distances from your operator to finite dimensional. How far it is from one-dimensional operators, two-dimensional, three-dimensional, etc. And to the operators of finite rank. It's clear that if in your infinite dimensional space, you want to invert operator, which is of finite rank, it's very bad. You cannot do this. It hasn't almost the whole space, it is kernel. It's kernel. And the smaller the rank, the worse it is. It's like trying to invert diagonal matrix, which has most of diagonal entries very small. Numerically, it's unfeasible. So that's why we have instability and low resolution. It's essentially the same thing as no propagation of singularities. Now, so what you want to have a method which is simultaneously had good contrast and good resolution. Unfortunately, the life is unfair. There are essentially no such methods. Those that have good resolution, they have bad contrast, and vice versa. And the reason physically is clear. To have good contrast, your medium, your body, should interfere significantly with the radiation. But in order to have sharp pictures, it shouldn't interfere. For instance, if it scatters your light significantly, then you don't expect to see sharp boundaries. They blur. So physically, it's explainable. So what can we do? And here is, as always, I probably will be able to do this, only this part. Hybrid methods of imaging come into play. For what does it mean, hybrid? It means that you know, for instance, that light has fantastic contrast, like 400%, 500% between cancer and healthy tissue. But it has awful resolution, almost no resolution at all. So what can you do? You could try to combine these two types of waves, namely, either one wave triggers completely different physical wave, or it modifies this different kind of physical wave. And the first and the best studied and the most implemented now is thermoacoustic tomography. And the idea is the following. So what you do, you send very quick electromagnetic pulse. It's either light of appropriate frequency or microwaves. So you send this very short, nanosecond long pulse through the body. Let's say it's a breast. The intensity is so small that there is no harm done at all. Then it goes through, and at each location, little bit of heating, it creates heating. So you send light or microwave, little bit of electromagnetic energy is absorbed here, and you have heating. The more energy absorbed, the more heating, and we know when you hit something, it extends. So you have extension starting at each point, which is essentially a pressure wave. Now, where more energy was absorbed, and this will happen in cancer, it will absorb 4 or 5 times more energy. Correspondingly, you have much higher pressure. So what you turn off this pulse in nanosecond, but ultrasound wave is pressure wave is propagating. So what you do, you listen, you put transducer here, which means essentially microphone, and listen to the sound. And essentially the idea is that what do you hear at certain moment? At a certain moment t, only the signals from the points at a fixed distance reach your transducer. Essentially, this distance is proportional to the time of observation, and coefficient of proportionality is the sound speed. So the longer you listen, the deeper spheres you know. So essentially what you do, you measure unknown. So the unknown function is the pressure at all those points, P of x, F of x. F of x is the pressure created at the point x. What you measure integrals of this function hidden inside over those spheres. Not all spheres. If you could get all spheres, it would be very easy problem, but you are sitting outside, so the only spheres you are allowed to use are the ones sitting on the boundary, on this so-called observation surface. And now forget all this medicine and physics, mathematical problem. You have a function f of x hidden inside of an object. You know all its integrals over spheres centered at certain surface around it. Radii are arbitrary. You can listen for a long time, for as long as you want. But locations of centers only here. And this working with PDEs, with wave equation, you know the role of spherical means. But here we deal with restricted spherical means. Namely, the centers are restricted. In wave equation, you need to deal with all means. And so this is fine, very nice mathematical problem, mostly resolved, although some issue remains. However, look, it looks like I cheated to you. I told you that we are looking for coefficients of some PDE inside. Where is the PDE? There is no PDE. Well, I was indeed cheating, And if you know wave equation, you should realize that I was cheating, since the spherical means don't actually give you the solution of wave equation. They are related to solution by some well-known, like Kirchhoff, Poisson formulas. So they are related both ways to the solution, but they're not the solution. So the truth is that you have this wave equation, C is the sound speed, and there are initial conditions. One is the unknown condition. The initial pressure wave is what we are looking for. We don't know it. And one can argue that in this experiment, the time derivative at the origin is 0. I will not get into that explanation of this. So you have the following problem. You have, let's say it's in 2D. I cannot draw 4D. So this is time. This is the space of locations. This is our observation surface. Oh, and I forgot to say what we know. We are looking for f of x. We assume that sound speed is known, or sound speed is known. So f is unknown. And what we do know, we measure the data on this surface S, we can measure for all times. So we know the solution on the side cylinder, but we don't know it at the beginning. That's what we need to find. So the problem is, knowing this kind of boundary data, find the initial condition. Hold on, it's impossible. It's idiotic, since the standard theorems for wave equations say that boundary and initial conditions are almost independent. There are only some junction conditions that they have to satisfy on the boundary here on the circle, but otherwise they don't know about each other. So for instance, if initial condition is 0 near the circle, this is essentially more or less arbitrary. So we try to do impossible. This, what we measure, has no information about initial condition. Are we stupid or what? The error is that it's not a boundary value problem. There is no boundary on S. The wave propagates in the whole space. S is made completely transparent to the waves. So there is no boundary here. The wave is in the whole space, and the boundary is artificial. We think it's observation surface, not the boundary. Now, how does it change the situation? It changes the situation very simply. It almost immediately implies that there is uniqueness of reconstruction, that we do have the data. And let me explain. This is all about so-called Huygens principle. So what we suppose that there is non-uniqueness. So in other words, from observation data on the surface, G is on the surface, I cannot recover this F. By linearity, we know that this means that there is an initial data F such it produces 0 observation on the boundary. I claim that if you observe 0 here, I shouldn't use the word boundary on the observation surface. Then F should be 0. Why? Look, according to Huygens principle, the initial condition compactly supported in a compact domain, it starts spreading wave. In particular, known estimates tell you that when time is going on, the energy goes to 0 in this domain. The wave spreads, less and less energy stays here. On the other hand, you didn't observe anything here on the boundary. But why don't you treat it as boundary condition 0? The US on S is 0 for all t. We didn't have real boundary, but if you observe nothing, this means that you have Dirichlet condition. But then the same standard theorem tells you that if you have these Dirichlet conditions, the energy should stay constant in time. So it should stay constant, but it decays to 0, so it is 0. So this explains why this thing is actually possible. And this shows that you need to make transparent boundaries. There is other, one can explain this also through spectral theory, which I will not do. There are many reconstruction methods. There are exact formulas, which are very nice, but they are known only from some very special observation surfaces like spheres and cubes. Moreover, it requires constant sound speed, which almost never happens. There are eigenfunction expansions. You expand into eigenfunctions of appropriate Schrödinger operators, and they are nice. Everything is okay, except that if you need to find numerically many eigenfunctions and eigenvalues, which for variable speed is questionable. And there is something that is easy. Look, what we just concluded, that if you have the energy staying inside of the cylinder, goes to 0. So let us wait for sufficient time till this energy here, let's say this is time t capital. There is almost nothing left. You can estimate this time. That there is very little left. So approximately we can assume that everything is 0 here. So now what do we know? We know the boundary conditions, G. And you know initial condition at the time t capital. Wave equation doesn't know the direction of time, so you just shoot backwards. And after time t capital, you recover the value here. Its simplistic approach is the best. It works numerically as a dream, and it's stable, and it's better than anything else we know. Well, I will drag probably till 50 minutes, sorry, but then I can say about. So I gave you a glimpse on hybrid techniques. So the hybrid techniques can take advantage of two waves. Ultrasound that we measured has high resolution, but low contrast. But we sent light, which has highest contrast, but no resolution. Together they have both. However, did we actually find what we wanted? No. In terms of acoustic tomography, we didn't find the quantity. What did we find? If you recall, at each point X, we found how much energy was absorbed. But what we wanted to see the optical feature of the medium. In other words, we wanted to see the light absorption coefficient, sigma of X. But how much energy is absorbed proportionate not only to sigma, but also to intensity. If you deliver twice more intensity of light, twice more will be absorbed. Therefore, h of x, which you recovered, is the unknown sigma that you're looking for, times intensity, which you also don't know. And intensity, unfortunately, satisfies an elliptic equation. So now, if you want to find sigma, you need to find an intensity. You need to find the coefficient in this equation, an elliptic equation. Well, it is bad, since we are sitting on the boundary. But hold on, this function h of x is known through the whole body. For every X, you recover the function. So what you have, you are sitting on the boundary, you don't have any spice inside. This H of X is your spy. You know this function, which is a highly nonlinear function of sigma that you want. You need to solve this equation and plug solution here, then you get H. But it is known everywhere inside. So we have internal data. And this should help. And it does. And it does. Let me give you just one example. This is, these are electrodes, and I send electric currents through the body and measure voltages. And as I told you, it has awful resolution. I showed you the pictures. Now let's do the following. Let's send acoustic signal, acoustic wave from outside. And let's focus this. It's physics question how to do this. Let's focus it at certain point X. Send focus ultrasound beams that will focus here. It will change a little bit the body, the conductivity of the body at this point. It will change your electric output. And you know that this change came from this point. So if you now scan, if you move your ultrasound to a different point, you get electric response, which also changes, and this change depends to this point. So what you get the data that depends on locations inside, internal data. You have a spy inside, and look what happens. This is a phantom, not a real patient, as you can imagine. And this is its reconstruction. You remember I showed the blurred image, no shapes at all? But this is when you do it with ultrasound. Well, it's not realistic since there was no error. Here we added to error 50% of noise, which unbelievable high percentage of noise for this case. And it's almost perfect reconstruction. There are other techniques like that. I will not go into this. I will spend just a couple of minutes to tell you something else. So I already addressed briefly hybrid imaging, how to combine good contrast with good resolution. I mentioned internal data, that internal data stabilizes, makes your problem reasonable. By the way, I didn't say why. There is very nice micro-local analysis of Fourier and pseudo-differential operators that tells you why and which internal data stabilizes the problem. It can tell you how many measurements you need to do. Maybe one measurement is not sufficient. It tells you make 3 of special kind. So, but I will not get into this. It's micro-local analysis that gives you data. Now, just a couple of words about noisy problems. There are problems when the noise is very high. This happens in medical imaging, in so-called SPECT imaging. Exactly, you remember when I told you that you give the patient radionuclide, very weak, so you want to know where and how strongly it shines from inside. And this is a machine, the SPECT machine. Now, this gate, both of those, they are emission problems, where you have the source hidden inside. You don't know where it is and whether it is there at all. You only measure what comes out. So the first observation is that for that, unlike in previous problems, if your detectors are here around the body, it's not sufficient to know where a photon hits them. They need to be able to tell in which direction photon came. Why? The reason is very simple. in this two-dimensional picture, you look for a function of two variables inside of the body. But you see, you are sitting on the boundary, which is one-dimensional. So if you only know the intensities of the hits at those locations, you know function of one variable. That's insufficient. You need to know the direction. How it is usually done? Usually, if this is your detector, they put thin lead tubes in front, so-called collimators. And what happens if your photon comes in a wrong direction? It doesn't come through. Only when it comes through one of those thin tubes, it comes through. So this gives you the direction. However, it kills majority of the signal, since most photons will not go through. Therefore, if you have very low signal with huge noise, after collimation, you have nothing. So what is done instead? There are so-called Compton cameras, which can detect direction without collimation. Unfortunately, those cameras, if your photon came in this direction, this camera cannot tell you exactly the direction. It can tell you that, look, there is this surface cone, and your particle came somewhere from this cone. But it doesn't collimate and therefore doesn't disregard any particles. Essentially, what mathematically it does, it doesn't tell you the direction, it tells you integral of your unknown function over a cone. So it tells you integrals of your function over plenty of cones. You can count the dimensionality, you will see that the dimensionality of set of those cones is higher than... Oh, I'm finishing. So this is highly overdetermined problem, and somehow it saves the day. Okay, now the last slide. Thank you very much for your patience and for this invitation. And I'm done.
Okay, well, thank you, Professor Kuchment, for a very nice presentation.
Many thanks.
And well, okay, questions, please. You can raise your hand here in Microsoft Teams. Please, questions. Meanwhile, may I have one small question? You said about that you measure operators and results of your action of these operators. So maybe in what spaces, what kind of spaces you're working with? Spaces or functions on the boundary or inside of the body?
You know, although I started from Banach space theory, eventually when I shifted to PDEs, and especially linear PDEs, I don't deal with any complicated spaces. My spaces are just all Sobolev spaces.
Okay.
Of the standard Sobolev spaces, but it doesn't matter that much. The answer will not depend that much of that. It's just more or less whatever spaces are, you usually have embedding theorems that tell you that singular values decay. What is it's just embedding theorem.
So taking more sophisticated spaces will not improve result, right?
I doubt this. I doubt that it can improve results. Okay. Since so far it works pretty well in micro local analysis in Sobolev space category, and unless we are pressed significantly, I'm not claiming that it's not needed, but maybe if you have some a priori information about where singularities to expect, etc., you can tailor your spaces to the data you expect to see. Such information can be very useful. But
by the way, do you use any localization principle? any kind of localization theory?
You mean localization in what sense? In spectral or in
I mean,
propagation?
when you draw your pictures and study the action of your operators, etc., do you care about the global situation, or you just do local analysis? Clear near to the boundary.
Well, to recover, to reconstruct, you need theoretically. Oh, that's a very good question. Since so in particular, you can ask: do you need? I don't know whether this is a question. Do you need to see the whole boundary, or some part would be? Yeah, that's a great question. I didn't say anything about this. The answer is yes and no. There are two theorems. One, both correct and provable. One, pure mathematics, that in most cases, in most types of imaging, it is sufficient information. And it's provable, sometimes very hard to prove. And another theorem says that you cannot do this. The reason is that you can prove that this will be extremely unstable. So most of the sharp features you will not see. And the reason is very simple. I told you that it's about seeing singularity. So you have singularity here inside, and it propagates nicely to the boundary, but you don't see this part of the boundary. Then you will see only some parts of sharp things. Like there is this inclusion, you will see, let's say, only this part of it and this, and those will blur and disappear. So this is very important question. In practice, very rarely we can see from all directions. Like in breast mammography, you cannot.
Does it depend on the shape of a body, whether the answer is positive or negative to this question?
Oh, sure. So, sure, it's also a good question. For instance, in X-ray picture, imagine that you can observe only some angle of X-rays.
Mm-hmm.
The answer is, here is your boundary. Only the parts of the boundary which you can touch tangentially by those rays you are visible.
Oh, yeah.
Everything else is not visible. There are very nice theorems about it.
Okay. Okay, guys, please, more questions. More questions, please. We have a very nice presentation with nice pictures.
I have no question, but I like you. I like to talk very much, and I would like to have the files which Peter will send you, Alexey.
Yes, we will put on web page, and with permission of Professor Kuchment, we will also put on web page the video demonstration. If you will have his permission, that we will do this, of course.
Okay, because this
is very recording me, but I give my permission.
Okay, thank you very much. So we will put on. We always put on our web page. We always put on our web page presentations and video lectures, so you can see it any time.
Yeah,
okay, more questions. Yeah, more questions, please.
Петр, я извиняюсь, а можно объяснить в нескольких словах, в чем состоит вот математически обратная задача?
Well, what is inverse problem mathematically? The general inverse problem?
Ну вот конкретно эта задача о нахождении, так сказать, что, восстановлении тела или, я не очень понял, чего-то по теплу. В чем она математически состоит?
Oh, that's exactly what this thermoacoustic tomography is. So that's the problem that I described. You have a solution of wave equation. This is time. This is space, which exists in the whole space, but you observe it for all times on some surface. You have transducers which are transparent for the waves. They don't obstruct the wave, so there is no boundary, but though it can be done optically. That essentially, why do I say here the heat? Since what we created heat inside of the body, and what we are listening to the sound. And mathematically, is this the following problem: that you have solution of your wave equation, with some sound speed, and you measured it on some surface for any time you want. You don't want to measure for too long, since some physical effects start just destroying it, but in all cases you can listen for practically for infinite time, at least for sufficient time. And so what you have the values of this solution on S. You have on spatial NS for all t. And what you looking for, the solution is when t is 0. So you want to find the initial condition from those boundary observations. And the trick is that it's not boundary. If these were actual physical boundary, you cannot do this. But the wave propagates freely, and so the simplest way to understand that it's possible, what I said. So mathematically, this is the problem. You have this equation, you observe for all t on certain surface, and what was the value at t equals 0. By the way, since closed surfaces are not always possible, you might want to know what kinds of surfaces give you this uniqueness. It's not completely solved problem. Mark Agranovsky contributed a lot. It requires algebraic geometry, but for practical purposes, this is good enough. So here is the problem. So understand, Mark? And the simple way to do this, to wait sufficiently long that the solution is essentially 0 here and shoot back. Solve. Now you have full initial boundary value problem. This boundary value shoot back till you reach the bottom. Is it clear?
Окей, thank you. Но это как бы не спектральная задача. То есть спектральных данных здесь вообще как бы нет. Только есть решение и по информации.
It is spectral problem. It is spectral. That's also a question. One of the best approaches is to take Fourier transform with respect to time. And then you have a spectral problem for Laplace operator or weighted Laplace operator in this domain. And essentially things boil down to geometry of nodal sets of eigenfunctions of Schrödinger operator of Laplace. And this is what Agranovsky and Quinta did. This is what leads to algebraic geometry, etc. There is a lot of spectral theory here.
Okay. Thank you. More questions, please.
Thank you.
More questions, guys.
In class, when I teach a class and there are no questions, I tell them that there could be two reasons. Everyone understood everything, or no one understood anything, and usually it's the second.
No, actually, it was very nice presentation with a lot of pictures. And
okay.
Well, from the beginning, I would guess that you will use Redon transform, but now you're speaking about Fourier transform.
Oh, Redon, you see, in this, I covered a lot of ground. In some problems, you need Fourier transform, in some X-ray transform. In most cases, the Redon transform is not the correct tool. It is what you see radon transform, if you have transport equation, which is a PDE inside of the domain, what you observe on the boundary is radon transform of those coefficients inside. That's how radon transform arises. But the trick is that the main role is of the PDE inside, which is hidden. And in many cases, in some cases, for instance, the works by Buchgame and others, there were problems dealing with radon transform till we came to the backs, to the origin, which is a PDE inside. So the radon transform is kind of a shade, a reflection of the more, as a deeper and more important PDE inside. So radon transform is used, but this is in a very in the simplest situations. Here, for instance, you cannot use radon transform.
I see.
I love radon transform and done a lot of work with it, but it has very significant limitations. Okay. Yeah, you get transform on geodesics, which is also only reflection of a PDE inside. So PDE in the interior is the main thing in all those inverse problems.
I see. Well, thank you. Thank you. Well, if there are more questions, please raise your hand. I don't see questions. We had, as I said, very nice presentation and discussion after that.
Thank you very much.
Please, everyone, we are entering the holiday season, so all the best in the new year, and please turn on your cameras. And as usual, we want to speak to our speaker. Thank you very much.
Thank you.
And